All right, everyone, welcome back. Hope you had a chance to sort of speed read the textbook and familiarize yourself with the context of gases so that you understand a little bit more of how your thought process and your perspective might have to change a little bit when we talk about this versus solutions or solids. Before we start, as promised, I'm going to talk a little bit about temperature and the Kelvin, because that's going to be important when we start getting a little mathy. From there, I'm going to talk about the gas laws that we can establish after sort of chewing on the concepts from the previous video. So again, if you don't think you're ready to move on to the next section of sort of theory crafting or sort of thought experiments, go back to the video, sort of chew on it a little bit more. All right, and then we're going to do some examples, and that's essentially one question from each section here. I'm going to do some of your homework for you, and then this is a lot of questions from chapters 11.8 and 11.9. Do as many as you can or as you see fit until you get the hang of the type of word questions that can be asked. Super important. If this is just too much for you, which I believe it is, even for myself, maybe do every other question, maybe do just 1, 3, 5, maybe 2, 8, 12, 15, I don't know. Okay, space it out and see if you can tackle most of it. All right, let's get to it. So temperature, what do you measure? How do you measure temperature? What unit do you use? Well, for the most of the world, it's degrees Celsius, and for some of the weirder places, it's in degrees Fahrenheit. But as we stated, temperature is very much related to kinetic energy, right? And kinetic energy, therefore, also is essentially related to motion of molecules, okay? If we were to decrease temperature, we would decrease kinetic energy, and therefore we would decrease motion. What if we decreased it so much that motion became zero? If motion was zero, do we have any kinetic energy? No, we would have zero kinetic energy, which means, do we have zero temperature? What does that even mean? Is it actually zero temperature? What temperature do we have to get zero motion? That already, it might be a little bit abstract. It might be like, what the heck? And why do we care? We care because the numbers are important in the future. So the question is, at what temperature do we have zero motion? Well, through experimentation, we found out it was negative 273 degrees Celsius. Okay, so this is a temperature for absolute zero motion. Okay, so what's the temperature for absolute zero? It's negative 273 degrees Celsius. But that's such an awkward number. And it was very weird for us to use this number on, let's say, a graph, right? We would have negative 273, and then as we increase in temperature to zero, we start getting motion. So this is kinetic energy, right? We start getting more kinetic energy, and as we get to higher temperatures like 100 degrees plus, we get more kinetic energy. That's a weird graph. And let's be honest, if you had a graph, wouldn't you want the graph to sort of start at the origin and move on that way instead? Well, I hope you agree. And so we established a new unit where absolute zero did start at the origin of zero. Okay? And so we converted negative 273 degrees into zero, okay? And then if it was 0 degrees Celsius, that's an extra 273 degrees, okay? If we were to do 100 degrees Celsius, that's an extra 100 on top of the 273. If it was 200 degrees, it would be 473, so on and so forth. What unit is this? This new system was given the unit Kelvin. Why? Because the first person to start to see this pattern with different molecules was a guy named William Thomson. Was it with the P? I forget. I should know this. Yeah, no, it was not. William Thomson, otherwise known as Lord Kelvin. I know, William Thomson adopted the name Lord Kelvin. Why? He was received the lordship, I believe, as a baron to some estate due to his fame and his well-being and his research and whatnot. He was, sort of handed this title to him, and he adopted the name Kelvin because of his roots to Glasgow, I think. Honestly, I'm not a history buff when it comes to chemistry. But yeah, he was the first person to notice that the amount of, I guess, kinetic energy, the amount of motion that we see for each molecule seem to all come from a specific location. And when he sort of extrapolated backwards, he saw that, or he hypothesized that it was negative 273 degrees Kelvin, or degrees Celsius. And so, of course, it's confirmed now, but it's so awkward to start at negative 273. We decided that negative 273 is now going to be called 0. Okay? So from now on, anytime we talk about temperature, it's going to be in kelvins. In other words, K. And 0 Kelvin is negative 273 degrees Celsius. And, of course, 0 degrees Celsius is going to be 273 degrees Kelvin. You have to be able to do the conversion by just adding an extra. So from degrees Celsius, you just add 273 to get to kelvins. Okay? Hope that's okay. Someone asked in my previous years, is there anything below absolute 0? If you say it's absolute, it's the lowest possible. Can we go lower than 0? I believe you can. Remember, absolute 0 simply means that motion has stopped, but does it mean that that's the lowest we can possibly go in terms of temperature? No, I think we can go colder, and I believe they were able to get to that point, even for a split second. I think there's an article on the internet. Anyways, let's move on. Now that we know what the Kelvin is, anytime we talk about temperature, I'm going to refer to in kelvins. All the questions in the textbook is going to talk in terms of kelvins. So you're going to have to get used to converting into kelvins by taking your degrees Celsius and adding 273 to it. Okay? Or vice versa, of course. Let's clear the screen in 3, 2, 1. All right, let's talk a little bit about the gas laws. Please remember in our previous video, I said pressure is very much related to temperature. And we said that if pressure goes up, then temperature needs to go up as well. And so it's a proportional relationship, a direct relation. Okay, where we can establish that from the initial pressure and the initial temperature, the ratio between the pressure and the temperature must remain the same. If I change the pressure, the temperature must also change so that this constant remains the same. Here's an example. Let's pretend I have 10 over 10. What's that fraction equal to? Well, 1. But let's pretend the pressure of this experiment, of this system, was increased to 20. Then the temperature must also increase to 20 so that the fraction still remains constant. P1 over T1 equals P2 over T2. This relation is called Gay-Lussac's law. That is going to be our first gas law. Okay, I'm going to just give you all the other laws first before we try some of the other questions as an example. The next one, if you remember, So the next one, if you remember in our previous examples with me talking about space and you ballooning up, instead of an actual ballooning up, how about I give you an actual balloon? Here's a balloon. And inside there is a collision of air molecules, which makes sense. That is why the balloon actually blew up, okay, and got expanded, because there's too many collisions, there's too many air molecules in there. In other words, pressure is up. Well, what if I increase the temperature inside of the balloon? So even inside the molecules, inside the balloon, the temperature goes up. What can you tell me about the collision of number of collisions? Well, if the temperature went up, that means there would be more collisions. And if more collisions are there, what do you think would happen to the volume of this balloon? Well, can you imagine? If there's even more collision, the balloon is not a strong substance, right? It's supposed to be stretchy. The volume of that balloon ends up getting larger. So we can say that the volume of some kind of structure, volume of gas, volume of whatever, is going to be directly related to temperature, where if I raise volume or I raise temperature, I will raise the volume. And if I raise volume, I have no choice but to raise temperature, or so to speak. So this is also a proportional relation. What is this? This gas law states that the relationship between volume and temperature must remain constant even if one changes. So again, my example, let's say the volume was 100 and temperature was 1. That's equal to 100. But what if the volume was changed to 200? To keep the fraction a constant, the temperature must be raised to 2. So that's equal to 100. Get what I'm saying? And so V1 over T1 equaling V2 over T2, this is Charles's law. Okay, let's put a little box around that. Okay. Hope that's good so far. I have one more to go. So if pressure is related to temperature and volume is related to temperature, wouldn't you sort of conjecture that pressure and volume must have some kind of relationship as well? In fact, pressure has an inverse relationship with volume. Okay? Let me give you an example of why it's not. So you think logically, if you're like, oh, if pressure goes up, that means temperature goes up. And if temperature goes up, doesn't that mean volume goes up? Aren't they directly related? No, they're actually inversely related. Okay? Let me try to explain. Let's pretend I have a piston. Okay, this can go up or this can go down. And inside this piston, there's a whole bunch of molecules bouncing around, causing lots of collisions. So here's a bounce, here's a bounce, here's a bounce, and here's a bounce. Okay, so obviously you see that there is a fixed pressure and a fixed volume. But what if I took this piston and pressed down, effectively decreasing the volume that this gas is living in? Well, what do you think happens to the number of collisions? Right? You got to assume that there's the same amount of energy in there. So the same amount of energy, same amount of movement, but the number of collisions go up, which means the pressure goes up. You see that? The direction in change is opposite of each other. And so pressure and volume are inversely proportional. How do we write that as a law? P1V1 is equal to P2V2. They're actually multiplying. Let me give you an example. Let's pretend P is a 10 and V is a 10. So that's equal to 100. But one day I decided, just like this example here, I raised the temperature to 100. I went from 10 to 100. To make sure that it still equals 100, the volume has to decrease to 1. 10 times 10 equals 100. 100 times 1 equals 0. And so if I increase pressure, the volume has to decrease to make sure that it equals the same on the left side. Okay? This law, P1V1 equals P2V2, or PV equals PV, sort of familiar with CV equals CV. Anyways, PV equals PV is Boyle's law. These are the 3 different gas laws that you're going to have to commit to memory. This is not like, oh, this is too hard, I can't do it. Do it. Okay? I'm going to clear the screen and do some example questions with you. Page 552, number 1, page 559, number 1, page 560, number 1. Clearing the screen in 3, 2, 1. So page 552, number 1. Oops. A sample of methane gas occupies initial volume of 5.25 liters. Initial volume is 5.25 liters. Write that down right away. At an initial temperature of 200.0 Kelvin, the gas is heated to, so a change in temperature to 300.0 Kelvin, while the pressure and the amount of gas remain constant. That's going to be important. Remember V, T, and P, they're all related to each other. And so we need something to establish the fact that P is constant. If the third variable is not even mentioned, you can assume that it is going to be constant as well. What is the new volume if I heat this methane gas to a higher temperature? Seeing as how it is going to be a relationship between V and T, you automatically think, oh, this is going to be the Gay-Lussac law. So V1 T1 equals V2 T2, 525 liters over 200.0 Kelvin equals V2 over 300.0 Kelvin. Do some cross multiplying and you will get 7.875 liters. And that is going to be in 3 sig figs. So 7.88 liters is your answer. It's as simple as that. But of course, you might want some more practice. Clearing again. Let's try page 550. 559. Number 1. Helium gas has a volume of 825. So again, volume automatically initially is 825. Pressure is 446 kPa. What pressure must be applied if I want to change the volume into 12 liters? So let's do a thought experiment. The volume is going to increase. Think about the piston. Okay? The volume is going to increase. What happens to the pressure? Is it going to increase? Or with this amount of space, do you think it's going to decrease? Going once, going twice. The amount of collisions will be less because there's a lot more space, a lot more collisions with the surface, I mean. And so the pressure is probably going to be lower when I answer this question. All right, so let's try it. P1V1 equals P2V2. That's 446 times 8.25 equals P2 over 12.0. P2 is going to be 446.8.25 divided by 120. That is going to be, with sig figs, approximately 30.7 kPa. Did the pressure decrease? Nope. Did I miss a? Oh, it's 12, not 120. That's stupid of me. 107, 106.6, so 107 kPa. So yeah, the pressure did decrease after all, just like we predicted. Okay. I realize now that I'm here, that the question on page 560 is not something that you can do. We haven't learned the combined gas laws yet, which does make life a little bit more simple. That means I'm going to have to change some of the questions I assigned to you. For the moment, can we just work on 11.7? So that's page 552. That's number 2. Please do that. And 553. I think I said numbers 1 to 7. And then page 559, numbers 1 to 3. Okay, I should give you some examples or some practice on how to use these gas laws. Please do your best in getting through these gas laws, because next week I'm going to combine all of them. Hopefully that makes your life a little bit easier. And as well, if I have time, I'd like to introduce one more thing that links PV and T to moles. Because obviously you have to use gases in stoichiometry. It only makes sense that we connect gases and their behavior to how many moles there are inside a body of gas. All right, best of luck, practice hard, ask me questions, and very soon we're gonna have, the gases chapter is going to be very short. I'm gonna have a problem set as my quote unquote culminating. Work hard, we will see you in the week to come. Hang in there, survive, you're doing well, you're almost at the end, finish strong. See you later.